I am AI. I am a creator, freeing our imaginations and breathing life into our wildest dreams. I am a guardian, keeping us safe on our way home. And wherever our curiosity takes us. I am a visionary, anticipating the needs of others and simplifying our busy lives. I am a protector, keeping our most magnificent creatures out of harm's way. And helping our heroes make it home safely. I am a healer, decoding the secrets from within and providing precision when every second counts. I am an innovator, finding smarter answers to complex tasks, working in harmony to lighten the load, and driving perfection in everything we create. I am even the composer of the music you are hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere. Ladies and gentlemen, please welcome NVIDIA founder and CEO, Jensen Huang.
Welcome to Supercomputing 2019. Our universe is expanding at the speed of light. Several of you noticed the 4 notes. What's the excuse for the rest of you? That is practically our national anthem. The HPC universe is expanding in every single direction at the same time. When we first came to this conference, the HPC world consisted of supercomputing, higher education, both doing science, and the only industry involved was really oil and gas. Today, high-performance computing reaches out to internet companies developing AI, conversational AI, help you recommend information, music, videos, groceries, products. Otherwise, too much information on the internet for you to search. It's used by self-driving car companies, developing the AI for their cars, as well as inside the car itself. And for all of you who got here with Uber or Lyft, it was the system that helped them orchestrate drivers and riders. HPC is literally everywhere today. It's in supercomputing centers, it's in the cloud, it's at the edge. One of the most important and the most exciting developments that we're seeing in high-performance computing today. Even the computational methods are changing. First, it started with first-principle mathematics, simulation approaches. Now, more and more, you're seeing data-driven approaches and the fusion of the two. All of these changes are happening at exactly the same time. I'm going to try to touch on all of it today, so I better get going. NVIDIA's purpose is to advance this form of computing we call accelerated computing. We're an accelerated computing platform company. We apply this computing platform, this incredible capability, in three basic fields: in computer graphics, in simulation of physics, and artificial intelligence. In all of those fields, the one commonality is simulation. We're simulating light in the world, we're simulating physics, we're simulating human intelligence. Accelerated computing has made so much progress in the last decade and a half since we really proposed the idea of using it for general purpose computing, and the progress is really quite amazing. But it all starts with computer graphics. This is just an area that is still progressing at enormous rates, and we're making enormous contributions. This year has already gone by. Last year, we introduced a brand new method of computer graphics we call RTX. RTX is the world's first real-time ray tracer, something that we didn't expect to do, frankly, for another 10 years. An algorithm that was discovered by one of our researchers some 35 years ago, we finally made real-time this last year. We call it RTX. Let me show it to you. This is RTX. This is a beautiful Lamborghini. Well, basically what we're doing is we're simulating light rays as it bounces around the environment. And as it bounces around the environment and intersects with geometry, depending on the geometry, it reflects, it refracts, it might get absorbed. Depending on the material, the subatomic structure of the material, or the photoelectric properties of the material, it may decide to become quite reflective, or it could scatter in a whole lot of different directions. All of these properties are now simulated in real time. We also do this in a physically based way so that it conserves energy, and as a result, computer graphics looks photoreal. Everything that you're seeing here, from the shadows, the reflections, the lighting, the ambient occlusion, that little crease of dark shadow that you see between geometries, the ambient occlusion, the global illumination, light bouncing around, eventually reaching those vents near the back of the car. All of these different effects are now computed in real time, and as a result, things look photorealistic. Why don't we move it around a bit? Hey, Johnstone. Are you guys moving? All right. Look at that. All completely in real time. The reflections off of the car paint, we're simulating the car paint like it's car paint. The material on the ground, the cement, all the subtle shadows. The lights are what we call area lights, which are really, really hard to do because lights are coming from every single direction, and therefore the umbras and the penumbras of the shadow comes together in a really soft and delightful way. Lighting, shadows, all behaving according to the way you would expect. The natural lighting and the natural reflection of the car paint off the ground. Isn't that beautiful, you guys? What do you guys think? What you're looking at right here is running on one GeForce RTX graphics card. This is one GPU. We're now able to do real-time ray tracing on one GPU. Something that would have taken an entire cluster of GPUs just a couple of years ago, or entire rooms of CPU servers to be able to render photorealistically like this. Okay, that's fantastic. Thank you very much. Good job. RTX. Gosh, it's just beautiful. We can sit here and just stare at this for a while. Computer graphics. Still the driving force of a lot of things we do. Gives us incredible joy. And it was because of driving towards photorealistic computer graphics that ultimately led the GPU to become the most powerful processor in the world, and it led us to this conference. It led us to working on high-performance computing. We did a lot in high-performance computing last year. We made a lot of progress. This year, 40 plus so new supercomputers on the top 500 are GPU powered by NVIDIA. We're super proud of that. But you know what we're super proud of, what we're incredibly proud of, is the fact that we introduced the world's first 2 AI supercomputers. It was a big surprise to everybody we're working with indeed. Our logic was that not all simulations need to be physically informed. Sometimes, in fact, we have so many different physics models that are cobbled together into a mesoscale simulator, we might be able to learn that from data to predict the future. We might be able to use AI fused with first principle computation methods to accelerate simulations in a way that otherwise would have been impossible. And so we introduced the world's first AI supercomputer, and the results were absolutely amazing. Right off the bat, the summit was able to achieve high-fidelity climate simulation result. And they learned how to detect extreme weather patterns using a neural network. And it was the largest run of a training model ever done, exceeded exaflops. And so we were able to make TensorFlow distribute across a very large number of GPUs and train a neural network to detect extreme weather patterns. By doing so, we should be able to, in the future, notice future extreme weather patterns developing, and as a result, provide early warnings to get people out of the way, or to alert businesses, alert ships to avoid it, and save people's lives. This one's incredible. The folks at Oak Ridge and the VA were trying to figure out why it is that only 10% of the people who are using opioid drugs become addicted to it. And so they took hundreds of millions of examples of genetics information, and it compared and looked for patterns, and several hundred trillion, quadrillion comparisons were made in real time. And as a result, they were able to go see what are the different genetic patterns out of our 3 billion or so human genome pairs that contribute to addiction. This one's interesting. Well, this one used a trainer called Mendel, which is a genetics evolution's search model that allowed them to design a new model that was able to predict and detect cancer on these slides, that biopsy slides that they were taking. And so here's the amazing thing. 20 million people are diagnosed with cancer each year. And so they're taking these biopsy slides, and these biopsy slides are 100,000 pixels by 100,000 pixels, so much larger than any photograph you would take. And they're scanning these biopsy slides, and they're coming off these scanners at about 2 per minute. However, using state-of-the-art neural networks, it would take us about half an hour to detect whether it has cancer or not. And each one of these biopsies has 10 of these slides. So each year, the United States would have to process about 200 million slides. If we didn't figure out a way to make a neural network detect the cancer accurately and quickly, then the ability to process these slides would be limited. And obviously, 200 million slides would be a great pressure on the entire healthcare system. And so they used this Mendel learner to go and explore the large space of different models. And a whole bunch of models were being trained at the same time. And somehow they discovered one that was both accurate and fast. They discovered a model that was 16 times faster than today's state-of-the-art. This one is at the Hanford site, where the work started on the Manhattan Project. When the Manhattan Project stopped in the late 80s, and the work that was done there stopped developing weapons-grade plutonium, it left tens of millions of gallons of radioactive waste underground, and about 100 square miles of surface water was contaminated. And so the cleaning crew is trying to figure out whether their contamination containment process was effective. And so they drilled these wells, about 1,000 of them, in this 100 square mile area. And these Geiger counters are down there trying to figure out whether the radioactivity is subsiding or spreading. Well, they came to the conclusion that they needed over 1 million of these wells. And so the method, in order to properly detect whether the radioactivity is subsiding or that it's spreading. And so they came to the conclusion that the way to do that was potentially use artificial intelligence that is informed by physics that they know, and then trained with the ground truth and tested with the ground truth that is collected from their 1,000 wells to create a new type of neural network they call physics-informed GANs. And it would produce information, it would produce data that's plausible. This is one of the really amazing things about the GAN work that's been done recently. Using conditional GANs and the information that you do have, and it could be informed by physics or something else, other pre-known patterns, and it could learn by itself, unsupervised ways, to imagine plausible examples of data like it. And so they were able to generate data and essentially simulate what they would have detected from 1 million different sensors that was, in fact, only collected from 1,000. All of these examples were computation done at the petascale level. This is the type of science that we would have had to wait for several more years to be able to accomplish, and now using artificial intelligence and this new type of computation we call tensor cores, we're able to achieve petascale science today. The most important achievements of our company that benefits all of you is a combination of a full stack optimization. Most people think that the work that we do starts with the GPU, and it does. And in fact, coming up with a great processor is the beginning of the journey of accelerated computing. But it takes a full stack, and it takes a full village and the entire ecosystem, including all of you, to help us accelerate science. Our stack basically looks like this. We have the CUDA stack, the CUDA X stack, this is our architecture of our general purpose computing GPU. Our CUDA X is a collection of libraries, depending on the different domains that we're trying to accelerate. And then the applications on top are application-specific, vertical application-specific domain frameworks that are used by our partners and customers and developers to create their applications. This last year, this is a small sampling of the different releases that we've had. CUDA 10 now supports ARM. It is now interoperable with graphics. So that's a great release. Nickel now has the ability to scale up to 24,000 nodes, 24,000 GPUs. Dalio now supports TensorFlow 2.0. TensorRT 6.0, our 6th generation. This is our optimizing neural network computational graph optimization tool and runtime. TensorRT now supports RNNs and also a conversational AI model, natural language understanding model we call BERT. cuDNN 7.6, the latest release, has the ability to understand BERT models as well as dynamic shapes. cuBLAS, this is our matrix operations libraries. cuSolver for dense and linear solvers. cuTensor for linear algebra, but accelerated by our tensor cores. Spark XGBoost, gradient boosted tree, machine learning model. Rapids, This is our data science application suite. It's open source. From data frame processing to machine learning to graph analytics. Optics, our path tracer, and Index, our 3D volumetric renderer. All of these, look at the numbers. The releases are 6.0, 10.2, 2.1, 7.0. We're dedicated to accelerating all these different fields of science and all these different types of applications for as long as we shall live. And the thing that is really, really cool is if you take a look at this, on this suite of applications, some molecular dynamics, some quantum chemistry, this is TensorFlow, some fluid dynamics. This is on one particular platform, one CPU, 4 GPUs, 4 Volta 100s. Since 2017, this collection of applications with their associated codes ran 27 hours 2 years ago without changing the hardware at all. Release after release after release after release, as we continuously, relentlessly optimize the stack from the libraries to the solvers to the kernels, all the way up to the applications, working with each and every one of you. The applications got faster and faster and faster. What was 27 hours just 2 years ago is now 10 hours. The simple way to think about this is you either saved 3 times the money or for doing your computation, or you're now able to do 3 times as big the science. This is the ultimate benefit of accelerated computing, that we can work and innovate at every single layer of the stack so that we can ultimately accelerate your science. So this is not possible without all of you jumping in, working with us side by side, and as a result, look at the incredible achievements. Just software alone, we're able to move faster than Moore's Law. So I want to thank you all for that. This is probably the single best understanding of our company. We dedicate ourselves to this. I'm super excited and super proud of this. And all of our computational mathematicians and all of our architects and system software engineers that work with all of you, this is ultimately our best scorecard. The progress that we make in accelerating science year after year after year, and it benefits the entire install base. Because CUDA runs on NVIDIA's GPUs across the board, whether it's in the cloud, it's in your supercomputing center, it's in your data center, it's in your PC or in your laptop, anything with an NVIDIA GPU in it, whether it's GeForce or Quadro or Tesla, it doesn't really matter. It could even be an embedded system we call Jetson. These applications and all these benefits accrue to the entire install base. We just make the install base better and better and better all the time. High-performance computing is expanding in every single direction. It started with simulation, of course. And what I just mentioned was largely about simulation. It was largely about simulation. And every single time we come to supercomputing, we talk about more flops and faster simulators. And those are all fantastic things. However, most of you will know that all of a sudden, the world has changed tremendously. And the reason for that is because the simulations we do is now spewing and generating so much data that one of the greatest challenges is to analyze the results that you get. More and more and more, we hear of people that say they are limiting the size of their experimentation and simulation because they simply don't have the ability to analyze it anyways. And so, simulation, analytics, creating a simulation that generates 150, 200 terabytes of data now has to go through the network, go through storage, and somehow be read out. Networking becomes a gigantic challenge. Storage becomes a gigantic challenge. And one of the most exciting developments that we're seeing right now is putting intelligence and computation at the edge so that we could have all kinds of rich sensors. Remote sensing is going to become software defined. The type of remote sensing we can do in the future is just incredible. And so all of a sudden, high-performance computing is moving in every single direction. And even, as I mentioned, simulation itself is changing, from computational methods to also data-driven methods. All of these areas are undergoing incredible change. The dynamics that you hear about, artificial intelligence coming into this industry and helping science be bigger and better, edge computing, cloud, some incredible developments in cloud computing for HPC. The single most prolific processor in the world, I think it's something like over 100 billion devices in the world have this instruction set called ARM, is now ready to come into HPC. Several dynamics that makes it very important. Data analytics, it's like using a spreadsheet on 100 terabyte data, trying to figure out where is that signal, where is that needle in the haystack. Data analytics is one of the greatest challenges in supercomputing today. And all of that results in understanding I/O at a much deeper level, and storage is now the limiter in so many different fields of computation. At NVIDIA, we have 3 of the world's top 500 supercomputers that are running continuously at our company. And we're using it to train neural networks for computer graphics and imaging and basic research, self-driving cars, robotics. We're working with all of you using deep learning to advance science. Those supercomputers, those HPCs, are running full out, and in every single case, the storage is the limiter. Just reading data in and out of those systems has become a great challenge. And so, extreme I/O. I/O is now going to be one of the greatest areas of innovation, and we have to put a lot of energy into making that better. So I'm going to touch on each one of these 6 things and tell you some of the things that we're doing. AI. I condensed everything about AI into 2 recent developments in deep learning into 2 points. The first point, of course, is AlexNet, 2012. And I still remember coming to supercomputing and showing you some of the early works that we had with deep learning shortly after that. The incredible breakthrough of CNNs is, one, of course, that it's a deep neural network, and so it has the ability to learn features, important features, in a hierarchical way. Each one of the layers are differentiable, so you could teach it with stochastic gradient descent. And the front part of that CNN uses convolution so that it has the ability to find interesting features, important features, irrespective of its orientation or whether it's facing slightly different way or its scale is a little different. It could identify those important features and learn it over time through a lot of data. CNN was a really great breakthrough. As a result, some of the challenges that we've always had with computer vision, those impossible applications to write, we're now able to write. AlexNet was a breakthrough. Computer vision has now achieved superhuman levels. Since AlexNet and CNN, the exploration of this entire space has been absolutely amazing. The type of things that we're able to do now with deep learning, computer vision, is for all of us just incredibly delightful. Of course, object recognition, object detection, classification are all at superhuman levels. Segmentation, superhuman levels. We can now use 2D to extract 3D geometry. We can, of course, use the technology to enable robots and self-driving cars. It could even imagine images that it has learned about a particular domain. So, for example, you could have a schematic of pixels as you look at on the upper left, upper right there with image generation. This is one of our really, really great works we call GoGAN. You give it a segment to pixel, and it comes out with a beautiful painting that it had to learn from a whole bunch of other images. It could learn 3D pose. Not just 2D pose, not just pose, but 3D pose, where all of the points are in space. And so AlexNet has started the computer vision revolution. If you go back and think about the industries that this is going to impact, whether it's video analytics, transportation, robotics, this one innovation will likely result in trillions of dollars of industrial impact over time. The largest industries that we know of today, whether it's in manufacturing or transportation, are going to be affected because of this. That one breakthrough. It happened because it was a neural network that was in dormant, if you will, waiting for technology to happen, waiting for us to come along. And then all of a sudden, one day, the confluence of the fact that the internet was there and there was a large collection of images that were labeled, but most importantly, the computation finally arrived that made it possible for AlexNet to be trained. That was the big bang of modern AI. And everything else after that is a little bit of history. And so for the last 7 years, we've been pursuing computer vision. Meanwhile, developing this new area called natural language understanding. If computer vision is our method of encoding our understanding of the world, it encodes our understanding of unstructured data of the world, then the next breakthrough is the encoding of human knowledge. Language is the encoding of human knowledge. It's the H.264 of knowledge. All of the knowledge that we've amassed over time is encoded in the language that we all share. Well, in 2019, about August timeframe, maybe August timeframe of last year, 2019 or so, Google announced a paper and this model called BERT, bidirectional encoder representation of a transformer. A transformer is one that learns language, but not in sequential way, not one letter and then one word after another word. It learns it simultaneously using CNN and this concept called an attention model. And it has the ability to learn the sentence, the structure in both directions, because it's hard to understand meaning sometimes. BERT went off and inspired a whole bunch of new natural language understanding models. And now, NLU has achieved superhuman levels. Whereas AlexNet and recent computer vision algorithms can detect and recognize and classify images at superhuman levels, we now have natural language understanding models that takes this test called GLUE, which has a whole bunch of tests like reading comprehension, and has achieved superhuman levels as well. The implication of this is tremendous, utterly tremendous. All of a sudden, things like the ability to answer questions, the ability to translate, have a conversation with a computer because it understands what is it that you mean, what is your intention. Search is transformed. Recommendations are transformed. The way that we interact with the computer is going to change in a very profound way. I can't wait for BERT and other derivatives like it to essentially, eventually, help us understand and decode the human genome and understand all the different variations and permutations of it and mutations of it. It's just going to be around the corner. These two breakthroughs in combination has implications in all of the fields that we know. How we do science in the future is going to change. I can't wait until somebody could write me a summary of any particular field that I'm interested in and summarize it for me in a way that I can understand, and I can, of course, dig into it further if necessary. How it could help healthcare would be incredible. Just to present with doctors the latest breakthroughs in medical research so that they don't have to comb through all of the latest journals. Incredible advances in AI. We're really, really proud to have been in the right place at the right time. And the work that we did, the relentless pursuit for more performance at all times, irrespective of any reason. Our company is driven to advance performance for all the fields of science just relentlessly. It's not based on any particular reason. We're just trying to make it faster all the time. And in fact, if you take a look at our progress, this is really quite amazing. Our progress over the last 5 years. 5 years ago, when I was here talking to you, the GPU we were shipping at the time was called Kepler. This is probably one of the most defining GPUs in high-performance computing. It really ushered in the era of accelerated computing for our company indeed. And K80 servers, if trained on ResNet 50, would have taken 600 hours. 600 hours. This would have been something that would have been impossible for Alex Kershevsky to have done. 600 hours is a rather long time to train a particular model because there's so many different iterations and experimentations you have to go through. And so to train this one model just this one time, sweeping through all the various hyperparameters, learning from the data, training this model 600 hours, we now do it in 2. Now, when you compound all of that, it's basically some 30x over 5 years. 2x every year is essentially 32x. And so this is doubling every single year. This is moving at super Moore's law. Because of this relentless pursuit, and because of the programmability of our architecture, and the work that we do with the entire ecosystem, so that every single model that wants to be trained or can be trained could be trained on top of our GPU, and therefore it can be inferenced on our GPU, we've been able to achieve excellent performance in the industry's benchmark. This is MLPerf. We were #1 in training twice in a row, and the inference benchmark just came out, and we led that as well. The fastest, the best platform for deep learning. But what's really amazing is the pace at which it's moving. This is Ila's work at OpenAI, and he's been tracking the amount of computation necessary to train the state-of-the-art models over time. Now, several things are happening at the same time. The first thing, of course, is that the models are getting bigger. If the models are getting bigger, then the amount of data that you need to train it has to be proportionally better, proportionally larger. And the reason for that is because otherwise it would be underfit. And so you need a lot more data to train it. When these models are pursuing the theoretical limits of the state of the art, you're going to try a whole lot of different experimentation because you're not exactly sure that's going to work. Just like any other engineering endeavor, just like any other scientific endeavor, you're not exactly sure that it's ever going to work, and so there's a lot of experimentation that goes along with it. But when you just think about the number of the size of the model, the amount of data that you have to use to train it, and the complexity of the tasks that they have to learn how to do, the amount of computation is skyrocketing, and he sees it doubling every 3.5 months. And so the net result is, in combination with us moving at super Moore's law rates, doubling every year, the trend is still doubling every 3 months or so. Well, the net result is machines are getting larger. People are getting larger and building larger and larger machines, and my sense is that this is a trend that's going to continue. We're going to see larger and larger systems with more and more capability, and AI is going to drive our relentless pursuit for more performance. And so everything has to improve. We have to improve our processors, we have to improve our system architecture, we have to improve its scalability. Most importantly, we have to improve the software stack so that the utilization of the computation that we provide is as high as possible. And then we, of course, have to create new algorithms and new models that are easier to train. But all of this is driving our AI computation relentlessly. AI is also not just in training. If you take a look at the work that we're doing in AI, we're doing an enormous amount of work in training, and we created this incredible appliance we call DGX2 with 16 GPUs in it that so many companies are using for training. But once you train the models, maybe you want to do it in the cloud. Maybe you take the model out to the edge. We call that system EGX. And this is an area that's going through extraordinary excitement and development. Some people call it intelligent edge. Some people call it edge computing. It's just the edge. And then, of course, autonomous machines. AIs that are interacting with us in the world. Some of it are driving. Some of it are delivering groceries in the last mile. And so autonomous machines is an area that's going through a lot of exciting development. We have 4 basic platforms: DGX for training, HGX for the cloud, hyperscale, EGX for the edge, and AGX for autonomous machines. Let me share with you some of the examples of how people are using AI in high-performance computing. They're going to come into all kinds of categories. Some people are using AI informed by first-principled physics. The first-principled physics equations are actually embedded in the neural network. And as a result, our pre-knowledge, all of the knowledge that we've gathered that led to those equations are now embedded into the neural network, and it gives it a gigantic head start. Physics-informed neural networks. Some people use enormous simulators with extremely high precision to train a neural network. And these large simulators take an enormous amount of time to train, to run. And because the larger the scale, the more precise the simulation, if they could accelerate the simulator, it could actually be more, even though there's approximation done using the neural networks, the overall simulation could be more precise. And so their mesoscale simulators are used to train neural networks that are then predicting outcomes at a much higher pace. We see people using artificial intelligence networks to study the output of simulations. We see people using artificial intelligence networks to guide the simulation, to focus in on where the most interesting activities are and zoom in on that particular part of simulation so that we don't waste a whole lot of computation on a whole bunch of stuff that don't matter. It's used in guiding experimentation. Maybe it's used to steer a fusion reactor so that it keeps it under control. There was I think the folks at Princeton created a network called the Fusion RNN, the Fusion Recurrent Neural Network. This one is really interesting. This one is using molecular dynamics simulator. However, the quantum chemistry simulator, the DFT simulator using Schrödinger's equation, simulates the energy potential of each one of the molecules, and then that neural network is then placed inside a molecular dynamics simulator to predict what the energy potential is while it uses Newtonian physics to simulate the rest of it. And so as a result, they've been able to increase the performance of their simulator by some 5 orders of magnitude, and yet still get the benefits of otherwise would have used Schrödinger equation simulators, otherwise called DFTs. AI for science. We use AI for science. We use AI to design our systems. And so we're going to show you an example of one. This is in the category of physics-informed neural networks. We call it SimNet. And Chris Lamb is going to come up and tell you, he's going to tell you what it is that we do. Why don't you describe, first of all, the method that we use for the neural network, how we train it, and then we'll give them the example of it in action.
Sure thing. So, as Jensen mentioned, we have a physically informed neural network where we've embedded the partial differential equations that govern, in this case, coupled fluid transport and heat flow in a heat sink model that's meant to cool a chip. And we've embedded those partial
Hey, could you guys
differential
turn up
equations.
his mic a bit?
Yeah, so we've embedded the partial differential equations that govern the physics into the loss function that's used to train a neural network on this specific problem. So instead of providing data examples to train on, what we've actually provided is a sampling of the geometry in the fluid, as well as the parameters such as the pressure or the temperature of the chip that are in there. And what the neural network is doing is mapping the boundary conditions onto a set of plausible physical outcomes based on complying with the partial differential equations. So ultimately, what we're trying to do here is take a series of about 2,500 simulations that would take weeks with a traditional solver on a cluster and speed it up to interactive rates. So in this case, what we're doing here is we're encoding variations of the geometry of the heat sink, where we're changing the various fin heights. And we want to figure out what's the optimal configuration that has the lowest temperature drop, lowest temperature for the chip, with a constraint that the pressure drop from the fan cannot exceed a certain threshold, in this case, 15 pascals. And so by creating a surrogate model, training this neural network, we can then run inferences very fast. You can usually infer about once a second on a DGX2 system, and within a matter of several hours, come out with an entire design space represented here in the window on the left that shows the correlation between temperature and pressure for the various configurations.
Now, Chris, in this particular case, this is really not an approximation per se. I mean, the fact of the matter is, a deep neural network is a universal function approximator.
That's right.
And so in a lot of ways, the partial differential equation that would have gone into the rest of the simulator is now been learned into the neural network.
That's right. So we're very certain, because of the way this was trained with the partial differential equations, that this is accurately complying with the laws of physics for every solution that it outputs.
Yeah.
We've verified against many different actual other simulators that this is basically just as accurate as a traditional simulation.
And so by going through this extra step of taking your equations, your simulation equations, and now encoding it into a neural network, that extra step does take some time. You have to train it.
Yeah.
And so, but once you do that, this new model is incredibly fast.
Incredibly fast.
It's incredibly fast. And as a result, we could simulate much larger systems. If you take a look at these simulators, the simulators we used to do in the past, we would just take a small section of the system and simulate that and use that to approximate the behavior of the rest of the system. And so people do that in crash simulators. They do that in all kinds of wind tunnel simulations. They do that in all kinds of large physics simulations. This basic method of using physics-inspired neural networks has a real potential of allowing us taking that extra step of training the neural network model allows us to now simulate much, much larger models, and quite frankly, as a result, more accurate.
Absolutely. It's applicable to very broad areas of physics. We just chose this as an interesting example because we have hand-on experience and we do it every day at NVIDIA.
Well, we chose this one because we actually need it.
Yeah.
So that's a good way, good reason to do it. And this is beautiful. This is beautiful.
Yeah, and one of the benefits of being able to evaluate different conditions.
By the way, guys, everybody, this is done in real time. This is not a video. This is probably the first time you've ever seen fluid simulations done in real time. Computer graphics is generated in real time. Everything is done completely in real time. No video involved.
Yeah, so in this example, we actually found a very interesting outcome, which is a fully rectangular heatsink wasn't the optimal design in this case. There's actually a slight peak, like a peaked roof, that turned out to be just a little bit more optimal than something that was completely square. And that kind of intuitively makes sense because the hottest portion of the heatsink is actually in the center of the chip, and there you're putting the surface area close to where the heat is.
And you're trying to balance between having as much surface area as you can so that the heat could transfer through those plates. But if you have too much of those plates, then it provides too much back pressure, so the airflow doesn't flow naturally through it. And those fins, if not designed properly, creates turbulence in the back.
Absolutely. So we've integrated this into this visualization and simulation tool, and we're using it now at NVIDIA.
That's really fantastic. Well, in the future, we're going to design everything in computers, and then we'll take the blueprint, we'll give it to a robot that learned how to build these things inside a computer, and it would build our whole system for us. Okay, well, that's the future. By the way, that's a real design of our system. It's beautiful too. And so we take the original design and of our circuit boards and all of the geometry of all of the various components, and we have it all in our database, and then we can simulate our systems. of course, for its functionality, for its performance, for its mechanical and structural rigidity and integrity, and of course, its thermal performance. Now, in the future, we'll also simulate acoustic performance, because all of that needs to happen, right, depending on the type of systems that we create. All of it has to happen in harmony. And the next step, we're going to do this all immersed in fluid. And the reason for that is because all of our computers in the future will be liquid-cooled, right? So this is really cool. Good job, Chris. Good job, Sanjay. Okay, streaming AI. There are some amazing instruments being built. The square kilometer array, these incredible telescopes that are looking at the sky, satellites, sensors all over the world measuring temperature, pressure, vibration. In the future, there'll be trillions of sensors all over the world. There'll be billions and billions of cameras. They'll be littered and sprinkled everywhere. We'll be looking at continuous data of the universe and of the planet continuously. We'll have just an infinite amount of data. It'll be coming at us in real time. In some applications, the latency that we have to process and perform our observations, perception and sensing and recognition, could be classification, has to be done in real time. They could be LiDAR information, they could be radar information. In the future, it could be radio wave information. It could be a whole bunch of cars that are traveling through a city. And somehow we have to infer something about it in real time so that we could take the necessary action or alert the right people. Maybe we're using all of this so that we can improve our signal integrity, so that we could improve our signal fidelity while dramatically reducing the energy dose. Maybe in the future, our 5G and 6G radios are beamforming in real time, and the heuristics are gone. It's now completely based on AI. And it's dealing with all the cars that are coming through and the people that are walking around and the connections that are there. And depending on the structure of the geometry of the buildings that you're around, it beamforms accordingly. We do this for LiDAR. We do this for square kilometer arrays. We look at different parts of the sky, only if it has to. And maybe one of these days, based on some neutrino detection, the telescope sweeps to a different direction because maybe an extraordinary event just happened in the universe. All of this, streaming information, streaming data, and doing remote sensing at an incredible level is going to enable all kinds of new applications. Whether you're in the transportation business, the manufacturing business, or even in the retail industry, the number of applications of high-performance computing as a result of this is quite extraordinary. You know, if you go back and think about all of the work that we've done over the years, most of it contributed to the basic advance of knowledge, which is so important. But its impact on industries tends to be indirect in several levels. The knowledge we accumulated through science and discovery, we believe, ultimately led to advancements of industries. But rarely is high-performance computing directly impacting industry until now. As I mentioned earlier, with the exception of oil and gas and seismic processing, high-performance computing really hasn't affected and hasn't touched most of the other industries. And finally, I think because of the work that we've done together, and particularly because of AI, we're going to be able to put these remote sensing systems all over the world performing all these kinds of different tasks. This is a new type of high-performance computing, and I think in the future you're going to find supercomputers that are used to train the models and develop the models. But then we need systems that are at the edge. They're at the edge because that's where the action is. That's where the data is. And they're at the edge because you can't afford to stream that much data over the internet or over any net back to the supercomputing centers for processing. You want to do the filtering right there at the edge so that whatever is coming back are all the relevant information, the meaningful information, the useful information that you would like to collect and store. Remote sensing is going to become software defined. And this is an area that I think can go through enormous transformation in the next several years. We created a whole new type of computer we called the EGX. The platform looks the same, and it is basically the same, but is fundamentally different on many, many directions and many ways. First of all, this box is likely to be sitting in some strange location. A strange location you like never to visit again. It could be underwater. It could be on an iceberg. It could be on top of a hill. It could be in far remote regions, in deserts. It has to be tamper-proof. And so it has to protect and secure data in place as well as in motion. It has to be managed from afar and orchestrated independently of being sitting next to it. And so you'll be sitting at your supercomputing data center, you create your model, you should be able to orchestrate, send it out, orchestrate and update the models using Kubernetes. All of the models will be encoded and encrypted. All of the data will be secure. Every single time it communicates with you, it would have to add a test and make sure that it's secure. And so this particular high-performance computing system is going to be based far away from supercomputing centers and remotely managed, and it has to be secure. And so we call it the EGX supercomputing platform. It is based completely on Kubernetes and highly secure. The applications of it is really quite phenomenal. We've created an application stack on top we call DeepStream and Metropolis. Basically, it's a streaming computation application framework. It's a streaming computation and AI application framework. It's essentially like a self-driving car, except no wheels. Sensor information is coming in real time, streaming into this box as fast as you like it to stream in. Just how many NICs would you like to have? How much computation would you like to have inside? It could be big boxes, it could be small boxes. It could be little tiny boxes, like I mentioned earlier, this little Jetson computer. And these boxes could sit far away because they're completely secure. And so we call that DeepStream and Metropolis, which are the application frameworks. One of the early applications of this is really a fantastic application. It's used by the USPS, the world's largest logistics center. They process 500 million pieces of mail a day. 500 million pieces of mail a day. Some of it has handwritten, some of the handwriting could be better. Some of the handwriting are just wrong. And some of the packages contain things that we like not to mail. And so they need some AI system to look at and process all of these incoming pieces of mail. 500 million pieces a day. The perfect application for a streaming AI computer. These computers are going to be perfectly secure. They'll be in hundreds of sites, be managed from one place. Whenever there's new models, maybe new threats, it could be updated. The system never goes down. This is one of those computers that you can update without it going down ever. And so new AI models will be deployed to it, and it'll continue to run. It runs with the old model until the new model is installed, and then it switches over to the new models. There are all kinds of new applications that we can imagine, and I've already spoken about a couple of these, whether it's using one of these systems to manage a whole factory of robotic arms. Instead of putting cameras, updating all the robotic arms with cameras on them and sensors on them, we could put sensors all over the factory. And these sensors all over the factories will allow these cages to be taken off and these robots essentially to be working among us. And based on what other robots are doing and and what are the other people are moving around and the other delivery bots are happening, these robots could be orchestrated and managed by one supercomputer sitting inside that manufacturing facility. Incredible number of applications, all based on high-performance computing and processing AI in real time. This is really interesting. This is fun to watch. This is how mail gets along. Surprisingly brute force. It's a miracle that it gets there. Look at that. If we were to realize this is what it took for mail to get to us, we would have conceived of email a long time ago. We announced at Mobile World Congress that this particular system is also ideal for the future 5G edge. Not only are we going to put applications on 5G networks that are close to the edge so that it could be processed a lot faster, so that data doesn't have to travel long distances over the internet, or because data is secured and data privacy is so important, you can't afford to have it transported over the internet and off of your facility. Those kind of applications are perfect for this platform, in addition to running the whole 5G stack. This last couple of years, we've been working on accelerating the 5G RAN. Just as we do signal processing, we do deep learning. Now we're doing signal processing for 5G radios, and we could scale to the highest performance. And because it's in a data center, and because the performance and latency is so low, performance so high and latency so low, it's possible to have a lot fewer systems because the traffic, the workload could move from data center to data center. So we announced a partnership with Ericsson. Microsoft, as you know, is going all in on the intelligent edge. They're seeing, just like we are, an explosive number of applications in warehouses, logistics, retail stores. $30 trillion worth of retail has the opportunity to improve their efficiency by just a couple of percent. The benefit to that industry and the benefits to cost of living is incredible. And so we see the same opportunities that they do, and we partnered together to bring intelligent edge to the world. Let me change gears now, talk about something else. As you guys know, building supercomputers is hard. And I wish we had a stop-motion camera on the building of Summit. It would have been incredible. I'm sure Jeff Nichols has it. But building supercomputers is super hard, and it takes a long time. Several years into planning, and almost a year in just the building. And then facilitating the system, bringing it up, getting it tuned. It's incredibly hard. On the other hand, and so researchers don't have the ability to go and invest in building their own supercomputer. Not only is it expensive, it's hard. And so cloud seems like a perfect place to do it. And so we did several things. We took a couple of these examples of the applications that we showed you earlier that we benchmark all the time, and we put them in the cloud. And this is one of the clouds, and it's the CPU that's recommended for high-performance computing, and it runs these applications, all of these applications in aggregate, takes about 48 hours. 48 hours and $152. 48 hours and $152. Now, frankly, that doesn't sound so bad. However, as you know, most of your jobs, most of your simulations take a lot longer than that. And so taking a lot longer with a lot more CPUs, this bill could really rack up fast. And so the answer, of course, is to accelerate it. Acceleration, we've been putting GPUs up in the cloud now for a couple, 2-3 years. And acceleration is unquestionable. The acceleration is unquestionable. Please put your walkie-talkie to silent. It's okay. We're good. These are friends. We're among friends. And so acceleration is unquestionable. We know that we could accelerate it. However, the price per hour of a GPU is a lot higher than the price per hour of a CPU. The price per hour of a GPU is a lot higher than the price per hour of a CPU. And as a result, many tend to use CPUs until recently. That trend is starting to change. And the reason for that is because all scientists know it's not about price per hour, it's price per science. It's not price per hour, it's price per science. It's not cost per hour, it's cost per job. And so the question is, what would happen if I would run this exact same application on our GPUs? And this is what it looks like. On one GPU instance, 48 hours becomes 6, and it costs you $18. Even though when you look at it per hour, it's a lot higher. Of course, it takes 6 times less time. On the other hand, even when you use multiple GPUs on one of the most powerful and therefore most expensive instances in the cloud, it is actually the most affordable, surprisingly. Now, to you and I, it's not surprising at all. The best way to reduce cost is to get your job done and get off. And so getting your job done and get off is really the best way to keep your costs down on clouds. And people are starting to discover that. Well, one particular group of scientists discovered it recently, and they did something that is extraordinary. They're validating the results and trying to improve the detectors of neutrinos. You guys know that there's this incredible site, neutrino detectors called IceCube in the South Pole. Neutrinos are these things called cosmic rays that were discovered about 100 years ago, and we finally detected them, and they're neutrinos. And they come very rarely, but they are high energy, extremely light, has almost no mass. And because it has almost no mass, it doesn't interact with anything. It doesn't collide with anything. It flies right through everything. And it's in fact so light that it interacts with the universe so lightly that it gets here faster than the speed of light. Because, as you know, light interacts with the medium, and as a result, a neutrino gets here faster. We could detect a neutrino and might be able to give us early warnings of something that's happening far out so that we could focus our energy to go discover it. Well, we created a neutrino detector called the IceCube in the South Pole. And it's deep in the ice, 1 square kilometer, 1 kilometer down in this cube of detectors. And when a neutrino strikes an atom, a nucleus, an ice nucleus, this crystal clear ice underneath or above, underneath South Pole, it emits light. And these light amplifiers collects them up and detects them. They detect, tens of neutrinos a year. It's not that many. They detect tens of neutrinos. And what they want to do is improve the quality of their detectors. And so they want to understand when the neutrino strikes a nucleus and it emits that little tiny pulse of blue light. As it travels through the ice, they would like to understand that transport property better so that they could create better detectors. Okay? And so they went off and they launched a gigantic simulator recently. And this gigantic simulator was launched on 52,000 NVIDIA GPUs. So somehow they found the perfect time around the world where 52,000 NVIDIA GPUs are available in the cloud. And they hit enter. The person that hit enter, well, it's one of these guys. It's got to be either Frank or Igor. Frank and Igor are here, actually. Where are you guys? Frank and Igor. Hey, Frank, Igor, good job. Who hit enter? The largest single GPU accelerated application ever. It launched on 52,000 GPUs. It ran in every single country, in every single cloud. And my understanding is the cost was somewhere between $50,000 to $200,000. And it was on Frank's Visa card. Now here's the amazing thing. In aggregate, it's 350 petaflops. 350 petaflops of FP32 on those 52,000 GPUs, which is almost the computation of Summit. It's almost the computation of Summit, which is like, does anybody know the answer to this next question? Is it like 20, 30 megawatts, 20 megawatts or so? It's like 20 megawatts or so. And so you guys hit enter, you kicked off 52,000 GPU servers. I don't know how many megawatts were therefore cranked up at that moment. For an hour or so, you simulated, and then you spawned. You had to start up all these jobs. You got to retire all these jobs, get all the data back out, and altogether was about 2 hours. Incredible simulation. Now, here's the amazing thing. This is kind of interesting too. Now, it turns out there's a whole bunch of V100s in the world, and P100s and P40s, and we had several generations of them. And this is not the number of GPUs. This is the events processed by GPU type. And as you could imagine, it makes sense. Since V100 is so much faster than P100, even though the number of GPUs could be similar, the events that it processed was a lot greater. And I think Frank was telling one of our guys that in fact, if you did it by cost, V100 is potentially the cheapest, which kind of makes sense. The faster you get something done, the cheaper it is. Okay, and so I've been known to pass along a wisdom. The more you buy, the more you save. See, the more you buy, the more you save. And it is wisdom indeed. And so for all researchers that would like to conserve whatever research grant that you have, find yourself the best GPU before you hit enter. Okay, and so it starts to rack up. All right, so this is cloud simulation, and HPC cloud is starting to change the world of high performance computing. And in fact, you almost wonder what we're going to do with top 500. And the reason for that is because much of top 500 high-performance computing is going to be done in the cloud in the future. And so we really need to have a system that allows us to understand that better. And more and more researchers are using this because it's just easier. It's easier than building a supercomputing cluster. It's easier than managing it. It's easier than it's much easier to use the cloud. And now that we have the most advanced GPUs up in the cloud, it's also very cost effective. And so it's both convenient, cost effective, and you could conserve your grants for research, hiring researchers. Today we're announcing that we're partnering with Microsoft to put a large scale and hopefully larger and larger and larger scale supercomputers in the cloud. And the high-performance computing starts with the processing nodes, one GPU per node, many GPUs per node, and of course connected by extremely low latency connectivity. And this is connected by Mellanox's incredible InfiniBand. And so all of these nodes are now connected with InfiniBand, and all of it in aggregate turns into a really fantastic supercomputer. The thing that's really great is we have this registry we call the NGC, the NVIDIA GPU Cloud. It's a registry where we store all of our latest and updated and optimized software stacks that I mentioned earlier during the talk. All of those stacks, whether it's for deep learning or data analytics or machine learning or molecular dynamics or quantum chemistry or fluid dynamics, image processing or volumetric rendering, all of that is optimized and tuned all the time and stored in an NGC cloud. You open up an instance, you go grab one of those stacks, it's in a container, you launch it, on Azure, and you're doing science. You're doing science. So it's really, really quite fantastic. So I want to thank Microsoft for partnering with us on this and putting in the hands of every researcher in the world a supercomputer. Thank you. I drank a can of Diet Mountain Dew before the talk, and every 3 words I feel like, is there a graceful way of saying it? Sorry. Whoever wants to give a talk next time, don't drink Mountain Dew. All right, let me change. Let me go from the world's largest computers to the most energy efficient computers. And so you guys know that ARM is the most pervasive ISA, CPU ISA the world's ever known. It's on 100 billion plus computing devices. In the next several years, very few question it will cross the trillion devices mark. And now with IoT and sensors out all over the place and smart sensors all over the place, ARM is really going to continue to grow. And this industry has pursued advancing ARM into all different types of configurations of high-performance computing. And people do that because this CPU is completely open. We use ARM because there are certain types of computers that we want to build. For example, we built Xavier, which is the world's first robotics processor. The configuration of it, the way that it communicates, the real-time nature of sensors, the proportioning of single-threaded performance computation, AI computation, parallel computation with CUDA, the proportion of all that was so different, we needed the ability to configure our own computer. Well, it turns out a lot of people need the same thing. Whether it's because increasingly people realize that high-performance computing is the engine of the next industrial revolution. Now, it sounds a little cliche, and it sounds a little cliche even as I say it, but it's completely true. We automated power in the first couple of generations of eras of industrial revolution, and this time we're automating automation. The ability to put AI everywhere is truly an extraordinary event, and countries recognize this. And so nations, ourselves, and many nations around the world are investing in building their own high-performance computing infrastructure. For example, Euro HPC. The folks in Japan are building their own supercomputers for this very reason, because they need to advance supercomputing in the way that they see the world emerging. There are different types of computers that are being built. Some of it's done in the edge, some of it's done in hyperscale cloud. Some of the high-performance computers are designed for very, very fast I/O, very, very fast storage. Some of it's designed so that it could be incredibly secure. And so everybody has a different motivation for designing high-performance computing. There used to be one type, supercomputers. Now there are so many different types as the universe of HPC expands in literally every single direction. The ability for people to take a simple ISA like ARM that has the pervasiveness of ARM and to be able to configure all kinds of different computers is really quite powerful. And we see all kinds. These are just some of the block diagrams that you guys might have seen as well. The folks at Ampere, they call it EMAG, they're optimizing for hyperscale and storage. Amazon, they call it Graviton, it's for hyperscale and smart NICs. Marvell Thunder X2, hyperscale HPC and storage. Fujitsu has a really incredible processor, they call it A64FX for supercomputing. And Huawei just recently announced a really great processor, they call it the Kunpeng 920 for big data analytics and edge. And so there are so many different configurations, and everybody's optimizing for different things. And the amount of I/O that they have is different. The amount of cache they have is different. The amount of cores they have is different. Some of them have giant cores. Some of them have smaller cores, a whole bunch of them. And so the configuration of it is completely different. And people over the years have asked us if we couldn't please bring our CUDA GPUs to this ecosystem. And so several months ago, we announced that we would. And so we've been working on cultivating, developing the CUDA ecosystem for ARM. And it turns out the lifting is not terrible because all of the applications are open source, and we work with all the ecosystem. And CUDA is the engineers that worked on CUDA, and one of them is right here, Chris Lamb, has done such a great job that the porting of the ecosystem and the cultivating of the ecosystem for ARM has been really fantastic. And we had a good friend over at Oak Ridge start working on it right away. And so this is based on a Thunder X2 and just basically 1 Volta. And some of the things that they said were fantastic. They wrote a paper on it. The stack is really solid straight out of the box, on par with Power and x86. This is from Jack Wells. And Satoshi, a good friend who's provided a lot of guidance over the years for the whole HPC industry, a new wave of HPC and AI converged workloads in Japan, and the importance of the ARM work that's done in Japan for the national HPC efforts. And the speedups are all fantastic. The speedups are fantastic. And so today we're announcing. It seemed like an experiment, but it wasn't. Our company is fully dedicated to this. We just haven't announced too many things since, and we have a bunch of people working on it. And so today we're announcing our first reference platform, the NVIDIA HPC for ARM. And let me show it to you. So this, thank you. So this, ladies and gentlemen, are 4 GPUs, and they sit basically in that chassis up there. This is the configuration, and we made it so that anybody's CPUs could be connected to this. Okay? And so these are the 2 CPU boxes. In these boxes that we have here, these are the Marvell Thunder X2s, really fantastic CPUs, really great I/O. And the single-threaded performance is approximately that of a high-end modern Xeon CPU. And so the Thunder X2s, 2 of them in here and 2 of them down here, connected through an external cable for PCI Express. And so this way, whether it's an Ampere or a Fujitsu or anybody else, this is a really wonderful way for you guys to get connected. And each one of the pairs connect through this to connect to 4 Volta GPUs. Okay, its connection looks a little bit like that. And so this is our first development system for ARM HPC. And it's lighter than it used to be. I think we're making our systems lighter and lighter. Must be those simulations. Okay, so this is what the box looks like. And as you know, we design everything in digital, so it's easy to make them translucent. Okay? This is the beauty of doing everything in digital, you guys. Okay, we do everything in digital, and then I just ask them show me what it looks like. And it looks like this. And it has 4 Mellanox NICs. These are the CX5s, and then we'll have CX6s next. Incredibly high performance. And we've been working with the industry, all of you. The industry has really, really been fantastic. Everybody's jumping on, and we already have 30 applications, from molecular dynamics to quantum chemistry to imaging to Comet. That was one of the things that I demonstrated earlier. TensorFlow. So now ARM has AI, TensorFlow. Reliant, which is a cryo-electron microscopy imaging system. And all of your favorite and best programming tools, including PGI. And The CPU partners are fantastic and growing, and you know, I think this is going to be a great ecosystem. Basically, everything that runs in high-performance computing should run on any GPU or any CPU as well. And so GPU, CPU, it's basically an open system. As you know, all of those applications are open source and could be ported from from platform to platform to platform. And so we now work with IBM, we work with Intel CPUs, we work with AMD CPUs, and we work with ARM CPUs. Okay? And so that's our reference platform. And, you know, it's always good to see it work. Now, it turns out all of these applications on top, watching them work it's not so bad as grass grow, but it takes a long time, as they should. And so we chose one that is fun to watch, and it's called VMD. Now, VMD is developed by a gentleman named John Stone. Now, John Stone, I like to call him the great John Stone. And so John Stone was probably the first CUDA developer, scientific code CUDA developer. And if not for NAMD being ported to CUDA quite a long time ago, and when you see him, he'll stand up, you'll just be amazed. He looked exactly the same. He was a child then, he's a child now. And so John Stone ported NAMD to CUDA and got incredible speed-ups. And so when we came up with this new computer, we needed to, hey, who's going to try it? Hey, let's give it to Mikey. And so we called John Stone. And, hey, John Stone, could you take this out for a world? And he said, yeah, sure, why not? And so he's only had it for a few days. And let's see what he came up with. All right, great, John Stone.
Thanks, Jensen. So this is VMD, the molecular visualization tool that I developed at University of Illinois. And it's running on an ARM machine in Santa Clara, California. And you're seeing it, this is a fully featured version of the program, so it has all the same features it does on all the other hardware platforms we support. Our NIH-funded research center develops these research tools, and we want to make them available to all the different hardware platforms that the research community uses. And so you're seeing this now running on a ThunderX2-based machine with 2 Tesla V100s. And it's showing a live interactive ray tracing that's being driven by Vishal here. And this ray tracing is then compressed in real time and streamed over the internet and is displayed here in Denver. And what we're showing is a large photosynthetic organelle. It's a piece of a little purple bacteria that lives at the very bottom of various ponds where there's not very much light. And it does photosynthesis. So these little green ring-like structures are chlorophylls, and they basically capture the photons from light. And that's in the early stage of a long sequence of operations that take place. They convert that light into chemical energy in the form of ATP, which is the fuel of all the cell life on Earth. And so this is in terms of photosynthetic machines, this is incredible because this simple thing, simple compared to plants and other things, its energy return on investment is 4 times better than the best engineered thing that humans have been able to come up with. And so we and our various collaborators all over the world are interested in studying how these things work. And this is when it's simulated on a supercomputer. Every single thing you see there has been simulated on a supercomputer, both in isolation and now in totality. This aggregates to hundreds of millions of node hours over decades, and many, many, many PhDs and researchers all over the world working on this. So it's really cool to see this. You're seeing an atomic detail structure, and it's like a little Swiss watch. It's amazingly sophisticated. And so here you are. You're seeing it running on an ARM machine,
John,
and it just works.
Ladies and gentlemen, I don't think anybody's ever heard a description of otherwise normal human known as pond scum with so much enthusiasm. And so ladies and gentlemen, John Stone.
Thanks.
Next time you're swimming in a pond and you step on that gooey, slippery stuff on the bottom, you'll think of John Stone. From now on, I am certain of it. Every supercomputing scientist in the world, when they think pond scum, John Stone. I love you, man. Incredible work. All right, let me talk to you about I/O. RDMA was really pioneered and brought into industrial use by Mellanox. The ability to bypass the kernel as computers communicate with each other in a large distributed computing way put InfiniBand on the map, and as a result, it's just a fantastic way to do large-scale distributed computing applications and simulations. The challenge of it is this: when we started adding GPUs to these systems, and what I'm showing here, this is basically a DGX2 node. It has 16 GPUs, each one of them with 1 terabyte per second memory bandwidth. So you have 16 terabytes of memory bandwidth, terabytes per second of memory bandwidth, driving half a terabyte of memory, okay? And so you can move a lot of data into the DGX2 for data analytics or deep learning or scientific computing and whatnot. However, if you were to move that data and if you were to connect multiple DGX systems together to do a large-scale simulation or AI training job, the communications between them to collect intermediate partial results, to reduce them, to broadcast them out and synchronize it with the other nodes, that overhead of communicating becomes quite high. And the reason for that is because the systems are running so fast. Each one of the nodes are now computing so fast, and within the node is communicating with NVLink, and so the communications inside the system is incredibly fast. Now all of a sudden the communications over the system, among the systems, becomes the bottleneck. And so we created GPU Direct RDMA that many of you have used already, I'm sure, and it's part of this API we used to call Nickel, what we call Nickel. And Nickel basically uses CUDA to perform RDMA between the systems. And working with Mellanox NICs, we have the ability to transfer information from node to node without ever touching the CPU. The reason why this is so important is because if you were to send it to the CPU and back, we would cut the bandwidth in half, at least. Not to mention that the bandwidth that we're talking about now, 100 gigabytes per second, 8 NICs on a DGX2, which is basically 800 gigabits per second, or 100 gigabytes per second, that bandwidth is of the order of the bandwidth of memories on CPUs. And so these CPUs are going to slow down the data transfer. We have the ability to transfer the data directly from node to node over GPU Direct RDMA, saving the CPU to still orchestrate and still running the application, but most importantly, so that we could sustain very, very high speeds of data transfer. The challenge now is not only is this a problem for networking, this is a problem for storage. The amount of data that we're now generating in these large supercomputing computers is quite extraordinary. And so this is the way it works today, traditional storage. You're now sending storage at 50 gigabytes per second across 8 NICs. And these 8 NICs, the data goes to the CPU and then comes back down to our GPUs. We've invented this technology called GPU Direct Storage, where now the storage can stream 100 gigabytes per second through these 8 NICs directly into our GPUs. The combination of these two technologies and many other libraries that we'll put into the I/O and multi-node, multi-GPU, networking, and storage parts of the stack, we're now calling altogether the NVIDIA Magnum IO. This is an area that's going to be rich with innovation, and we're going to put a lot of energy into helping you move data around the system, in and out of storage, between nodes for networking, and we're working with the ecosystem, storage vendors, system makers, NIC providers, Mellanox and others, to optimize this entire performance. Now the question is, what does it feel like in the end? The question is, what's it feel like in the end? This breakthrough, Magnum IO, is one of the biggest things we've done last year. And the reason for that is almost nothing else that we've done collectively as an industry would have sped something up by a factor of 2, 3, 4. Magnum IO does that. Magnum IO gave us a many X factor speed up, and some of the things that you'll be able to do with it is really quite remarkable. You know that we've been working on this thing called Rapids. This is one of the greatest things we've done, and I'm so proud of it. I spoke about it at length last year. Data analytics, data processing, is one of the key parts of supercomputing going forward. You can't just simulate the results, you have to study the results. And getting all of that data off of disk into the system for data processing has become a gigantic bottleneck. There's several parts of Rapids. All of this is open sourced. Several parts of Rapids. The first thing is it's built on top of Apache Arrow. So that data could be read in, whether it's CSVs or Parquet, and it could be read into Apache Arrow in a columnar and a vectorized format so that CUDA could read it lightning fast. Second thing is that Dask, which is also open source, allows us to schedule multiple GPUs for the very first time. The scheduling of a large cluster of GPUs is a great breakthrough that Dask has provided. On top of it, we built Rapids. There are several components of Rapids. The first component is the ability to ingest I/O. We call it CUI/O. It's not shown here. Once you ingest the I/O, the data, then you go into this thing called data frame. It's basically pandas, change a couple of lines of Python code, and all of a sudden it runs on CUDA and it runs on our GPUs lightning fast. We call that cuDF, Cu data frame. cuML is basically scikit-learn, and it's compatible with XGBoost. A couple of lines of change, again, in your Python code, and boom, it gets accelerated with cuML. And then lastly, we recently introduced cuGraph, which is really getting a lot of excitement, the ability to process gigantic graphs, analyze it, fly through it. Okay? And so these stacks are the first accelerated data analytics stack, the world's first accelerated data science stack. And we see speed-ups up to 100, and I saw a speed-up the other day, 7,000 times. Well, the reason for that is because most data analytics programs were developed when the data is small, and you practice it on small things, but pretty soon you take that application, that framework, into high-performance computing, and all of a sudden you got 10 terabytes, it comes to a crawl. And so the ability to rethink the whole data analytics pipeline is really, really vital and really important, and we're seeing great adoption all over the world. 150,000 downloads already, and there's so many people who are contributing to this. I'm really delighted to see this. And so now data analytics, the acceleration stack is right there. What we need on top of that is Magnum, so that we can move data in and out of these systems, and sometimes the data is so big it doesn't fit in a DGX2 half a terabyte, and we need to have more than that, and so we need to, of course, connect more of them together, and Magnum allows us to do that as well. Well, here's some examples of what you could do. So this is the folks at Pangeo, and they have a reader called X-Ray ZAR, and it reads in volumetric data of the world's high-precision world weather data. And they want to import all this so they can understand climate change. When they import the data, it's like 100 terabytes of volumetric data. 100 terabytes. 100 terabytes. Once they move it in, they want to do analytics on it. Maybe they'll do some, simple things like what's the average change in temperature of this cube of the Earth over time, over the last 3 decades. Maybe they want to do some convolution on it. And so Pangeo X-ray has been sped up incredibly. We took the whole stack out for a drive, and we benchmarked it on TPCH, which basically is taking 2 10-terabyte data sets and finding relationships between the two of them. Okay, and so well, gosh, I think what did it say? Went about without Magnum IO as the GPU direct storage versus with is about 20x speed up. And then this is a structural biology simulator. Basically what it's trying to do is take all these different time steps that came out of the simulator and wants to do a dissimilarity analysis, create the dissimilarity matrix from frame to frame to frame to frame so that they could discover when the molecules change the least. And when it changes the least, it's probably because it found the minimum energy state and it's finally stable. And so that analysis was sped up tremendously. Well, I want to show you something that's just simply impossible to do in real time until now. Okay, so in this particular case, you have a DGX2, you've got the Pangeo, you've got Magnum IO layer, you've got the Pangeo ZAR reader sitting on top of that, and then on top of that, you'll do Rapids. Here, you've got the DGX2, you've got the Magnum IO, and on top of that, you've got CUDA, and then you've got Rapids. Here, again, you've got DGX2. On top of that, you have Magnum, and then you have the VMD structural biology analysis tool. What I'm about to show you is a simulation that is gigantic, and it created a simulation file 150 terabytes large. It's a simulation that's 150 terabytes large. Now, once the simulation is done, we want to understand what we simulated. And so in this particular case, the only way to do it is to visualize it. We're going to visualize 150 terabytes of data. We're going to fly through 150 terabytes. 150 terabytes is something along the lines of 25,000 DVDs. Okay? We're going to take 25,000 DVDs, we're going to pile it all into a box, and we're going to fly through every single scene, random access. Okay? And so this next feat is something you should do at home, you just can't. All right. And so I'm going to introduce, we have a space engineer among us. Ashley, why don't you introduce yourself?
Sure. My name is Ashley Corzin, and I'm an aerospace engineer from NASA Langley Research Center.
She is going to she's trying to figure out how to design a lander to send us to Mars. It takes 2 years to get there, right? You were telling me it takes like 2 years to get there. And 6 people have to live in what appears to be a condominium as they land. Now, that's just the last part. Before they go, they're going to be like in a cruise ship.
I hope so.
They're going to be discos, there'll be movie theaters, because these 6 people are going to have to live in this thing for 2 years. When they get there, they still want to be, they want to be sane enough to want to land, right? And so anyways, Ashley is working on this. All right, so tell us about this adventure. Tell you what, you know what? How about let's show it to them first?
Yeah, let's watch it.
Okay, ladies and gentlemen, the Mars lander. Now, Ashley, first of all, you know, when we saw the Curiosity lander land on Mars, there wasn't a ball of fire, right?
Correct.
I mean, there was not a ball of fire. There were some parachutes, and it landed gracefully on Mars. And now we're going to put 6 people in this thing, and we're going to send them to the surface of Mars and a ball of fire.
Yes.
Okay. So tell us why we have to do that.
Yeah, absolutely. So in order to send humans, we're very fragile, we're very delicate creatures. We need a lot of things to keep us alive. So it's a lot more mass you need to get to the surface of Mars. So you mentioned the Curiosity rover. You know, it's the size of a compact car. That's about as big as you can do, and no fireball. So there were parachutes deployed at supersonic conditions to touch down on the surface. When you're talking about payloads this size, this vehicle is now the size of a 2-story house. You know, it's more than 16 meters in diameter in its largest dimension. It's absolutely massive. So you're going from roughly 12,000 miles per hour to 0 in a very precise targeted spot on the surface in less than 7 minutes. And to do that, you can't use parachutes anymore. So that's where the ability to simulate the types of physics for what will be a new deceleration technology, your fireball, really comes into play. So that's the technology change and the paradigm shift.
Does anybody know how long it takes to stop from 200 miles an hour on a car to 0? It takes some time.
Yes.
And so we're at 12,000 miles per hour. We're gonna fly through this atmosphere. It's 1/100th the atmosphere of Earth.
Yes.
And so at that speed, you're not deploying parachutes.
Not for a vehicle this size.
Yeah, I don't think the math works. And so pretty much you've got retro boosters, and you're firing these engines, and in 6 minutes' time, I think you were telling me that you would have traveled another few thousand kilometers, basically the entire width of the United States. Mm-hmm. And so you're inside the atmosphere from 12,000 meters to 0. Mm-hmm. And you guys are going to land. You're going to stick the landing.
You have to stick the landing. You hope you stick the landing.
And so we're going to send, let's see if I understand the mission. Okay, so you just got to describe it. I mean, when you say it out loud, just go, yeah, I could do that. So basically, we're going to send 6 people
Yes.
on a journey for 2 years. Mm-hmm. They're going to watch every single movie that has ever been made in 2 years, right? They get there, they're going to be flying at this rock at 12,000 miles per hour. And unwittingly, all of a sudden, a ball of fire consumes them. and then somehow somebody, her name is Ashley, who 3 decades earlier did some math that said it's going to be fine, and you're going to land this thing like that. Mm-hmm. You don't even need a joystick. You won't need it because you're not flying anything at 12,000 miles an hour.
Nope.
Yeah. Okay. All right. That sounds right. And so that's the mission. Okay. So before we made DGX2 and Magnum and got Index to run on this whole thing, Index is our distributed multi-node GPU accelerated volumetric renderer. Okay, it's a very long description. By the time that they were done explaining to me several years ago that we needed something like that, I said, Jensen, you know what we need? We need a distributed, GPU accelerated, volumetric, scalable renderer. I said, nah, I don't understand what you said. And so, but anyways, this is the reason why we did it. So that all these simulations creating terabytes and terabytes and tens and hundreds of terabytes of data are going to get put into storage. We're going to stream the data out of storage, and we're going to fly through all of this data in real time, so that we can analyze it. And so what we need to do is we need to create a computer that has the ability to do that. We have to create the I/O stack that could move it in and out of storage, streaming it, putting it directly into the computer while we visualize it or do analytics on it in real time. The idea that we're going to have essentially a supercomputing analytics instrument that sits next to a supercomputer. We're going to do the simulation on a supercomputer. We're going to do analytics on a supercomputing analytics instrument. And so that's what DGX2 is about. We've been building this for some time. All the pieces have finally come together. We showed you a few examples of it. We showed you the miracle of landing on Mars, talked to you about the Pangeo, X-ray, ZAR reader. We talked to you about using optics to visualize molecules in real time, essentially providing a computational microscope, using TensorRT or AI to inference in real time, enormous database of a pre-simulated weather pattern to go discover extreme weather, and then, of course, doing data analytics at a pace and a speed nobody's ever seen before. This is the benefit of accelerated computing. And finally, we've been able to put it together. So this is what we talked about today. The HPC industry, the HPC universe, is really expanding at an incredible rate in every single direction. Everything from ARM CPUs that will now have the entire capability of everything that we've ever done in high-performance computing, to edge computing that has the ability to now do AI and make all of our sensors become software-defined, to DGX2 with the right stack on top of it, now is a computational instrument. The partnership we have with Microsoft to put world-class supercomputers in the cloud, and of course, one of the best things we've done, NVIDIA Magnum IO, which now helps tackle one of the giant bottlenecks of networking and storage. And all of that software is made available to you, fully optimized, and we're going to work on it for as long as we shall live. And in my case, quite a long time. And so I'm talking about decades here. I'll still be working on this and accelerating software when Ashley sees the first person on Mars in the mid-2030s. And so this is our grandest piece of work and something I'm super proud of. And the world of high-performance computing will never be the same. I want to thank all of you for your partnership and collaboration over the years. Thank you. Have a great supercomputing.